Okay, I started recording. Caner Hocam, the stage is yours. Thank you.
Okay. So, hello everyone, good afternoon. So, I'll be mainly talking about small-scale inflationary fluctuations and their possible maybe observation through primordial black holes and like interferometer scale gravitational waves. So, this has been something I was a bit wondering. So, these are a couple of papers that I did with a number of collaborators. So, okay, I'll start with for like everyone from different maybe backgrounds, a little bit about inflation and scales of inflation. Then I will talk a bit about just one interesting mechanism, actually one of the most promising ones, how to produce some particles during inflation. It also could produce like during the evolution of our universe as well. It doesn't have to be during inflation. Then I'll touch a little bit these induced gravitational waves that could be probed by the current and forthcoming experiments, gravitational wave experiments, and how this could help us a bit to probe the high energy physics. And then I'll end up with some of these future experiments and how could they help us a bit understand the small scales of inflation, which has not been really probed until now in depth. Okay, so you can stop me at any point to ask. So yeah, please feel free. So, okay, the like inflation in the classical level is just a standard expansion of the universe with some accelerated expansion. A double dot in the the scale factor is larger than 0, so it accelerates. And on top of it, there are these quantum fluctuations imprinted on this background. And during inflation, as you know, these are the contributions from the gravitational side. Just these are the gravitons, the gravitational waves propagating degrees of freedom. And there is also, due to inflaton, there's a scalar degree of freedom, assuming you have like a single field, or you could also have multi-field as well, but this is the dominant density perturbations, or quote unquote scalar perturbations. So what people do now is the following thing. They compute typically using the CMB, largest scales of our universe, how these inflationary quantum level fluctuations leaving imprints on the observable, cosmological observables we do, like CMB anisotropies is one of this kind. So this zeta parameter is directly related with the density perturbation. So by reading these density perturbations from the temperature fluctuations of the CMB, you could read this primordial information. So these are 2-point functions. These are just propagators. Of course, one can go higher and higher order calculations, but until now, we only measure this guy, let's say. Gravitational waves have not been measured. As maybe some of you know, people are trying to see these B modes, which is this chirality of the CMB spectrum. From the polarization, they try to detect it. And the 3-point functions, of course, it's even harder for the gravitational waves, but the 3-point functions for this density perturbations are also still not measurable. Primordial one, though. I'm saying, of course, you measure some 3-point function, but the primordial one hasn't been detected. So what people do is the following. You have two quantized field, right? You can treat these guys, and then you end up with some power spectrum or propagator, which is parameterized in this fashion, some amplitude and some pivot scale. How does this guy scale? Like, how does this vary? It's the running of this parameter, and it's interesting. Yeah.
Can I ask you a basic question?
Yeah.
Yeah, I also started looking into this stuff, so I need to learn even the basics. But you know, at least in standard QFT, we usually use 2-point functions to fix the normalization of fields, right? So, like for higher functions. So here, for example, but it clearly 2-point function contains information. It like the amplitude, etc.
Just 1 second. You mean by fixing the? So okay, you can think it the following way: whatever field you quantized, When you impose the canonical quantization conditions, then you set kind of initial conditions for this given quantization field. But here, this number is tiny, 10 to the minus 10 or so. This includes some physical information, actually. It's not just the initial quantum perturbation info. It is, I mean, it is proportional to that. It's some up to proportionality constant. But it is not just the field quantization, I could say.
But how about like, okay, so how do we define this psi k? Like, okay, you give us the 2-point function, but
so you do, for example, you typically what you do is you have, let's say you choose as gauge. You don't have to, but at the end, this variable is a gauge invariant quantity. At the end, one way is, for example, very typical case. Let's say you set your spatial Hij part of or Gij part of your metric to 0, and then you can have these like in your metric you have the scalar part of your perturbations. Then you have it's directly proportional to the inflaton's value, like delta phi. Let's say you have a let's say we are doing a scalar field theory phi, right? This guy is proportional to, let's say, that delta phi. It goes like h over phi dot delta phi, but it's just detail. It's proportional to h over phi dot. Then when you quantize this delta phi guy by scaling with a, which makes it conformally like delta phi over a is that's the quantity you quantize actually. You impose the like a delta phi over a comma delta phi over a dot whole quantities. This is the kinetical term. You quantize that guy. You equate it to I times momentum conservation. That's the impose you do. Okay.
Okay, so that fixes the overall normalization.
Exactly. That sets the quantization, and there is an overall h over phi dot like and maybe in Planck as well somewhere, but there was also a proportionality. That's what I'm trying to say. That's why this number isn't just order one number. That's what I want to say.
Okay, good. Thank you so much.
Okay, yeah. So this is the same derivation. So like some power spectrum, dimensionless power spectrum, not for the scalar or density perturbations, but for the gravitational waves, so gravitons, okay? And these lambdas are their plus cross or left-handed, right-handed polarizations. Okay. So again, there is this is the parameterization of the guy, and it's just depending on the Hubble scale that inflation is occurring divided by the M Planck, okay? So you immediately realize if Hubble is large, we have more gravitational waves. Obvious. So these are the numbers that people measure, okay? So these are the numbers that are, I think this is the latest numbers. As you see, this is almost 0. And this ns minus 1 is almost 0 as well. You see, it's a very tiny number, 0.03. So there is almost a kind of, people call this nearly scale invariant spectrum. Okay. So when you compute this ns and PGV over P zeta, you come to this plot and check that if your model matches with the predictions or not. You take your favorite inflation model and then you check it. Okay. There are so many models. It's now you want to understand what is wanting to discriminate them is the R, tensor to scalar ratio. This is called little r, which compares the power in the gravitational waves to the power in the density perturbations or scalar fluctuations. This number is now bounded about 5 times 10 to the minus 2. And the third thing, when you come to this region, people will try to probably search for the non-Gaussianities in order to discriminate different models, because there are so many models satisfying these conditions. Okay, so now I want to touch a little bit of a thing that we do and which will be relevant maybe for also smaller scales. So we were wondering the following question. In the largest scales, there is this direct relation between the since the scalar perturbations have been measured, the R, tensor to scalar ratio, PGV, is directly going with Hubble scale, right? Or the potential of the amplitude of the potential of your inflaton field. And this is the light bound, how much your field occurs in the field space. So we were wondering the following question. assume there are other fields than the inflaton, which makes your universe expand, inflation accelerated fashion. But there are other things that producing gravitational waves, right? So that you can break this linear relation, which is this is a very famous relation, like, because the idea is whenever we measure this number, we immediately will have an idea in the simplest models of inflation, the scale of the inflation, which is now expected to be really high still, 10 to the 15 GeV range. Of course, it could be a bit lower, but this is now the typical range. And the question was like how you produce gravitational waves efficiently, right? At the end of the day, you need some HIJ, right? Because that's what you want to source. And you need some light fields, because if it's heavy, you cannot source the quadrupole. You need some light fields and source it. There are multiple interactions that people suggested. But since due to time constraint, it's already been 13 minutes. In order not to let behind, I'll just discuss this very briefly. So this is a interaction. I think maybe you also already discussed some axion field, which is a pseudo-scalar, coupling to a FF dual like a topological term, like Chern-Simons term. Okay, and this F is in units of energy. This is a dimension 5 operator. This is one of the first operators you can write beyond, like in the, what is it, that larger than dimension 4. Okay, so this is one of the terms you could expect to contribute first. The other thing you can write a chiral term for fermions, but I will not discuss that because these guys are gauge bosons, so you can produce them abundantly. For fermions, you're bounded by this Pauli exclusion, but during inflation, you can evade that, but long discussion. I'll just discuss how you can produce large gauge fields, and these large gauge fields, how do they source back both axion, and if it's your inflaton or not, inflaton field, okay? So that's the coupling. So when you write the equation of motion of the gauge field, so this is a chiral coupling. The helicities of the gauge field segregated have different signs for the two different helicities. So one of them has a plus, so it behaves like a positive mass square, as you see. But in one of them, it becomes a minus sign. This minus sign is interesting because it makes it unstable for some regime, okay? And this regime is around the horizon crossing. So when these gauge fields are leaving the horizon during inflation, like the space-time just grows, right? These guys, due to this tachyonic instability, they are sourced by the motion of the axion field. As you see, when this X thing, which is some pseudo-scalar, is constant, this thing is just, you can integrate this out. This doesn't change the equation of motion of anything. This is just a boundary term, okay? But when this guy is moving, which means you have some, so it's as you see a derivative, there's a derivative coupling. So for a constant shifts, this guy doesn't contribute anything. So there is this already this shift symmetry property of this coupling. But when this guy moves, say, let's say it has a continuous field, it moves under time, right? It rolls through, let's say, some potential. You have, which we define here as a Xi, some particle production parameter, let's say, call it. It's dimensionless. It produces abundant amount of particles, large amount of particles. And this could be very, I could say, expected situation. Of course, it depends on the strength of the coupling, but this behavior is universal. We will now try to understand how big this parameter should be so that we should observe. Maybe we never see it, or maybe we see it. So let's try to understand. But one thing is important here. So two things you should maybe remember. One, different helicities have different, let's say, mass square-like terms, and the one helicity stays in its vacua, right? Because you have a positive mass square, you cannot excite it. The other one, in only around horizon crossing, as you see around this K over AH term is order 1, which corresponds to horizon crossing, produces these gauge fields abundantly. So so there is this exponential growth of the vacuum state of one helicity of the gauge field. But this is interesting because you will see that since you excite only one helicity, it's a chiral enhancement. You will see that this chiral gauge fields also source gravitational waves chirally, and there will be some other interesting consequences. Okay, so this is one of the most interesting, one of the most interesting particle production and signatures of the axion interactions with the gauge field. So, okay. Here I try to describe briefly the situation. So assume you have this axion guy, and it has some potential coming from maybe different sources, maybe because of the instantons, maybe some other reason, and you don't have, like, there is this like a sinusoid, like a potential coming from the instantons. Of course, there are higher order moments as well, but because it has a typically potential sign, some integer number divided by 2 pi f, like a structure, but there are higher orders as well, but you assume they are suppressed. It's I should of course say that this is a bit phenomenological model. So the idea is the following thing: when our axion moves its in potential, right? When it has a non-trivial potential, we will see that this axion guy will be producing a gauge field, because this Kasib parameter producing lots of particles when this axion guys move fast, because it breaks this I mean, this sourcing term, this instability becomes stronger and stronger with the faster motion of the axion, because the gauge field source has been eaten by the sourced by the axion kinetic term. Okay, so these are for the perturbations. We source the gravitational waves through excited gauge fields due to in result of this instability, and of course we source all the other degrees of freedom as well. So the axion field could be your inflaton, of course, or could be any field. Like in all these like high energy theories, you could find abundant of these pseudo scalars. Like that's why people call this actually axiverse. Like it means axion universe. Like for these high energy UV complete or claim to be UV complete theories, you typically produce you have these like so many degrees of freedom, and you have a bunch of these pseudo scalars or higher number of these such type of particles. So these could be inflaton, or this could be some spectator fields, which means their energy density is suppressed. But still, you could see some signatures of this guy axion field on your observables. Okay. So okay, I don't want to go into extreme detail, but what I'm saying is, as you remember from the previous slide, you try to source this tensor to scalar ratio, gravitational waves divided by the scalar perturbation. So gravity waves divided by the scalar guy with extra sourcing terms, right? So there are contributions from the vacuum, but also there are contributions from this axion and the gauge field interaction. Since CMB scales, we know the fluctuations, density perturbations are highly Gaussian. And this sourcing term is the source fluctuations are highly non-Gaussian. You look for a region where your gravitational waves are sourced by such a mechanism, so that you break the relation between the R and the potential, like this gravitational waves and the potential, but also your majority of your scalar density perturbations are coming from the vacuum fluctuations, from the inflaton. Okay, so I don't know, here you see the gravitational waves in sourced or axion gauge field interaction divided by the vacuum. You see it could be order of really like hundreds or thousands. So you can produce so many gravitational waves with respect to vacuum source, vacuum production. But in the blue one, right, these are the scalar perturbations. These could be suppressed with respect to the axion gauge interaction. So which means you source lots of gravitational waves without spoiling the Gaussianity of your fluctuations. This is just like a model at the end of the day, but why we study this interaction was for two main reasons. One, pretty much everything else, when you would like to produce large amount of gravitational waves, you produce lots of also scalar particles, which makes your fluctuations non-Gaussian, which in this interaction, to my knowledge, this is the only mechanism. You can produce both gravitational waves, but without spoiling the density perturbations. And the second thing, this is the almost guaranteed interaction when you have a axion or like some pseudo scalar. Okay, this chiral coupling. Okay, some details, but let me just say the following thing. Our aim was the following. Is this relation really, really guaranteed? Which means when people tell you that we measure the gravitational waves or the tensor to scale ratio, are we going to be saying immediately that this is the scale of inflation? That was the question. So is this relation there or not? That was the thing we tried to challenge. We tried to test if this is always the case. So it seems in such models, it is possible to source gravitational waves dominantly and not touching too much the scalar perturbation. But this is still scale dependent process, okay? If people could measure it for a long region of the scales, then you can understand there could be such a mechanism really sourcing the gravitational waves, and then you can understand the scale of inflation. So this such interactions could make you think that the scale of inflation is much higher than its origin. And one interesting sign of this is the axion gauge interaction, because remember, this is the chiral coupling. That's why the produced gravitational waves are also chiral. So if you could measure some statistical parity violation, then boom. So this gravitational waves should be sourced by some chiral process. And we know that almost any astrophysical process could produce such a thing. It's only possible by high energy and cosmological stochastic backgrounds. So that was something we studied for the largest scales of our inflation. But now I would like to take you to the heart of the topic, what I was a bit curious. So any questions up to here? No? Or any? Okay. So the heart of the topic is the following. All the things I discussed a couple minutes ago are based on the CMB and large scale measurements, okay? We measure all the inflationary signals at these scales, but this is the whole scale of inflation. So you produce quantum fluctuations at all these scales, but we only could measure these scales. From here, the clusters, galaxy clusters start, even smaller scales start, you cannot measure, they're extremely nonlinear. So there is a hope that these chemical potential of the photon, cosmic microwave background could extend our measurement to some extent, maybe possibly next generation experiments, but still there is a large, like a fraction of the scales of the inflation is not properly. So what is interesting with primordial black holes and gravitational was this. So CMB and large scale structure covers 10 to the 3 order of magnitude scales, but inflation is 10 to the 26 amount of change in the scale. Or if you take in the log space, right, it corresponds to about 50 to 60 e-folding number. So we only probe 7, 8 e-folds here, and we probe, let's say, about 10 e-folds or so, I guess. Yeah, 10, 12 e-folds here. So in total, it's a 20, 25 e-folds, maybe at most. But the rest 40 e-folds, this huge fraction of the universe is unprobed. Okay, so maybe primordial black holes and gravitational waves could tell us a bit about that. Any questions here? Okay, so at small scales, you have slightly more freedom, because remember, we could produce maybe gravitational waves by some interactions, but also you can produce scalar particles as well, or density perturbations as well. There are no strong bounds like those scales. So maybe this axion and the gauge field interaction, this natural thing, could maybe some signatures at smaller scales as well. And if the density perturbations are also enhanced considerably, maybe it can produce primordial black holes. It also produces large amplitude gravitational waves, which are stochastic and possibly chiral. Then if we could see any sign of this, it could be maybe a smoking gun. We could then suspect, oh, these large number of these scalar degrees of freedom, maybe they have really some role at the really high energies of the energy scales of the early universe. So, okay, we play the same game, right? You enhance the amplitude of these gauge fields by this tachyonic instability from the axion and the gauge field interaction, axion FF-dual-like structure, and then you can source your inflaton field and also your axion field. So here there are some bounds on the amounts of primordial black holes with respect to their masses, and here the bounds on the amplitude of the scalar perturbations as a function of the number of e-folds. These are the bounds, okay? And when you do that, you choose some specific type of statistics, because I'll come to that point. The statistics of the fluctuations is important in the primordial black hole formation. Okay, so there are three main scales now, which people are trying to add more, that people are trying to probe the gravitational waves. One is this famous LIGO. I think everybody knows about this guy. Now the Europeans are trying to do this LISA experiment, a laser interferometer space antenna. And then there are these pulsar timing arrays, and its next generation is called SKA, square kilometer. So this is corresponding to nanohertz scales, gravitational waves. The main aim is probing, let's say, 10 to the minus 10 to 10 to the minus 7 or so hertz. The LISA is going to probe the 10 to the minus 5 to, let's say, 10 to the minus 2 hertz range. And the LIGO, as you know, between like 1 to 100 or 1000 hertz range. Okay. And of course, their sensitivities are different. Here in all these three plots, you see the y-axis is the omega gravitational waves, which is the energy density in the gravitational waves with respect to the total energy density in our universe, or critical one. But our universe energy density is close to the critical one. And the x-axis is the frequency of these gravitational waves, okay? And on these left plots, we study the scalar side of the story. What is the scalar side? The scalar perturbations, scalar quantum fluctuations, which of course become classicalized after the inflation. This time, more convenient time variable again, or variable is this again, number of e-folds until the end of the inflation. And the y-axis is the 2-point function again, p zeta. You remember from the first slide. So, this axion gauge model could have this one degree, one freedom. There's a one free parameter. You can, depending on the speed of the axion field, remember the kinetical energy of the axion field sources the gravitational waves and also the gauge fields. These guys could pick any of these scales. Of course, it's a bit phenomenological model. We just try to show that even without violating the primordial black hole amounts, right? These are the bounds on the primordial black holes coming from the scalar perturbations. We can produce gravitational waves that could be probed, that could be seen by these experiments. So it seems for PTA and SKA experiments, like pulsar timing arrays, this is possible to see this signal, and also, of course, LISA. But the story isn't like this is not possible for the advanced LIGO. Or LIGO scale. So even if you saturate the maximum amount of perturbations, you cannot be able to see any signal at the LIGO scales. Okay. So since we touched this PBH a lot, let me try to go a bit more in-depth intro to that part. So this is an old idea, okay? It's not just come to people's mind yesterday. It's an old idea over how many years? Maybe almost 50 years. So the idea is in the early universe, much before the CMB radiation released, Hawking, Carr, and then many people have considered that after also inflation idea, that maybe with some large density perturbations, there could be some black holes very different than the stellar ones could be formed, okay? So you can have some topological defects, some maybe bubble collision could form it by large density regions like this areas, or during inflation, you can enhance, amplify your density perturbations, which for some scales, not all the scales, but for some scales, and those scales could produce some primordial black holes of some given mass, okay? So there are abundant way of producing primordial black holes. If you think in terms of inflationary way, like if you're an inflation person, typically you think that your zeta or density perturbation parameter, curvature parameter, is larger than some critical value, okay? And what you do is the following thing. You integrate the probability distribution of this stochastic variable, which is has a quantum origin, is larger than this critical value, and you integrate over it for larger values so that you find the chance, the probability for a given scale, the forming a black hole. Okay, is it clear? Because this is important. This is the kind of heart of the PBH formation.
Can I ask a question?
Yes, yes, please. Because
how do you define that the quantity that you evaluate in the integral. I heard that it had a quantum origin, but can you give a little bit more details so
Sure.
we can understand better?
One thing you should be careful is the following thing. So you understand, right? The story is the following thing. If you have a perturbation larger than some threshold, this object collapses, right? This number is found by some simulations or whatever. Assume now, just at the theoretical level, you try to understand what fraction of your horizon, what fraction of the universe will turn into a black hole. So this P is calligraphic P is not the power spectrum. This is a different guy. I think I will touch this here in this cartoon, but let me try to say a few words here. This is the probability distribution function. When you integrate this guy, right, it gives you what? It just gives you 1, right? Assume like you have the standard inflationary scenarios. This guy is typically a Gaussian thing, right? Because what is a free field probability distribution? It's just Gaussian. It's a free field, right? It's a Gaussian variable. So it's e to the minus x squared divided by 2 sigma squared and some normalization. The sigma there, which is the variance, is your power spectrum actually. Okay. Let me go here then. Okay, forget about this orange and the blue. Just look at the red one. Okay, is it visible now clearly? So you see there is a Gaussian distribution, right? When you, and this is your variable zeta, your curvature perturbation. When you take the 1-point function, the expectation value of this, right? This is 0, right? For a Gaussian variable, it's just 0 here. But we compute, of course, it's true for any quantum object, right? When you have just one raising and lowering operator, right? When you evaluate it around the vacuum, right? Or in the bracket, it's just 0, right? This also should be giving you exactly the 0. That's why this is just some Gaussian. And remember, how do you define a Gaussian? 2 variables. One, expectation value, the average, right? Central value. Mu, like typically people write mu, and the other one is the standard deviation, how this width is changing, This width is actually the power spectrum variance of your value, which means when you close your eyes and you have a pocket, you would like to take a zeta value, let's say. This is the square root, you take the square root of this variance or the standard deviation, right? This is what it means. So each time, since this number is about 10 to the minus 10, each time this zeta, when you take a typical value for the zeta, is 10 to the minus 5, right? So what you do here is for a given some threshold, you try to integrate some given threshold, zeta critical, for a given scale, you have some probability distribution, you try to integrate the area under this. So what possibility you have your zeta is larger than this? Is it clear now?
Yeah, it's way more clear now. Thank you.
Okay, great. So this is a probability distribution function, okay? And you integrate over the chances of zeta for a given k. So this is just a random variable if you want to consider like a random what was this probability theory, right? You try to integrate over some tail, okay? And this tail is set by this critical parameter. Okay, so you immediately understand, right? The primordial black holes, when they are formed during radiation domination, are only tiny fraction of the total universe's energy density, but they are dust-like structures, right? They are non-relativistic. So as you know, non-relativistic guys have like a scaling a to the minus 3. They are just like dust. They just scale with the volume. But radiation goes like extra redshift of the frequency, right? Or wavelength. So for radiation, the energy density scale 1 over a to the 4. It scales faster, right? It decays faster, energy density. So when you have radiation and matter, right, the relative energy density of the matter with respect to radiation grows with scale factor. So even if you start with small number, 10 to the minus 10, 20, whatever it is, during this radiation dominated era, these guys' energy density with respect to the radiation grows. So they could be some fraction of maybe dark matter, or even if not, some small fraction of it. These guys could have some energy density during the in the current universe. And final thing I would like to stress is the mass of these black holes are directly related with the horizon size of the scale that they enter the horizon back. So let me try to explain this a bit better. In standard astrophysical stars, right? It's completely different story. How they form a black hole is a completely different story. At the end of the day, their pressure couldn't be able to beat the gravity and they collapse. Here in early universe, the story is a bit different. So when you have assume a large density perturbation, right? Some fluctuation coming from the tail of the sky, some large density perturbation, right? And this perturbation starts to collapsing, right? What do you expect? What would be the, and it's almost horizon size. As you see, almost all the causal horizon collapses and forms a black hole. So there is a one-to-one relation between the large density perturbation scale and the mass of the black hole. So almost this whole horizon, when this whole perturbation enters the horizon, it collapses, forms non-linearly, boom, like a black hole. So this is a different formation of mechanism for black holes. This is happening in the very early universe, of course, hypothetically. So, and immediately you can relate this to the wave numbers or equivalently frequencies or equivalently the E-fold number of the universe, inflation. So you can, there's a one-to-one matching between during what period of inflation there's a large density perturbations and the PBH amount, okay, or PBH, given PBH mass. So you know from the given scale, you know how big this perturbation size is, and then you and this immediately turns into a mass of the PBH. Okay. Any question up to here? These are the, I could say, heart of this topic. Actually, these 4 bullets. Okay. What is their abundance? What is their mass? How do they grow and how to make them? Okay. So these are the 4 main points. And now there are 2 interesting intervals that primordial black holes could be some fraction of our energy density of our universe. This is this 1 to 100 solar mass, finally astrophysical black hole mass range. And the other one is this extremely light region. And it's just a pure chance. When you would like to produce these primordial black holes, you produce gravitational waves inevitably, I will discuss in a second, at PTA scales. And when you would like to produce these guys, you produce gravitational at LISA. So we will conclusively probe these interesting possibilities with these 2 experiments in near or some kind of a bit longer future. Okay, so this was the cartoon. I'm happy that it is useful in understanding. I try to discuss here. Assume you are given a Gaussian random variable and how you form some bounded object or compact object from that, given some critical value. But I also discuss with different colors the following thing. Assume you don't have a Gaussian, but a bit shifted or skewed Gaussian. You play a bit, you deform your Gaussian shape. You see, you can play a bit with this corner because remember, this number is tiny. 10 to the minus maybe 20, maybe 10 to the minus 15, maybe 10 to the minus 10 or whatever, okay? So even if a little bit skewness, a bit change in the shape, especially very important for the tail. And this tail is the part forming the PBHs. So for primordial black holes, the tail physics is important, probability in the probability distribution function. Okay. So here chi-square is the, when you have a 2 variables, both of them are behaving Gaussian and you multiply them. And they're behaving, probability distribution behaves like chi-square. And when you have 3 fields, like let's say phi cube like thing, and phi is let's say some Gaussian field, their phi cube like operator behaves like Gaussian cube, cubic Gaussian shape. And this is a different probability distribution because interactions deviate from the free field properties, and also it changes your probability distribution. Is it clear for everyone? Then I will continue. Okay, I hope it is clear. So this is one thing I would like to very briefly discuss. So there is a slight difference. There is a relation, just actually this is an exact relation. When you would like to compute density contrast, which means the background density and how much excess you have it, which means rho minus rho bar over rho bar, to inflationary fluctuations such a way. Typically, when this zeta is really tiny, it behaves like, as you see, guys, it's just the Laplacian of the zeta. It's like the standard, actually, it's the standard thing that we have. Remember, in also electromagnetism, we have that. You take the Laplacian of your potential, you end up with some source. It's exactly the same with the gravity as well. You have this delta square zeta, and you have some source, because this is behaving like the excess matter. But the funny thing is the following thing. This primordial black hole process is really highly nonlinear thing. It's not really trivial. This zeta typically at CMB scales is tiny, 10 to the minus 5. But when you would like to produce primordial black holes, this number is order of 10 to the minus 1. So you start getting suspicious that all these factors could be important, because when this number is too tiny, it's just 1. You don't care about any of these. But when it becomes order 1, right, close to the 0.1 or so, this could be really not easy computation to do, because if you go higher and higher order terms, it could be a bit non-perturbative. And unfortunately, it is. When you try to attack this problem perturbatively, you will realize that it's not really easy. You cannot just put here, let's say 0.1 or whatever, okay? It's not possible. You don't get the proper calculation. All the higher terms will contribute. But you can start from two main techniques that people study bounded objects. They typically do these for the galaxies or whatever. I'm not expert on that. But thanks to this project, actually, I learned it. For typically structures, people use two main techniques. One is this something called peak theory. What you do is the following. You count the density of these peaks, okay? You try to find maxima in a random field, and then you count these density peaks, and you integrate over the ones who are larger than some threshold again. So this is based on this counting these peak numbers, and how much of these black holes you will have. Other technique is called threshold theory. This threshold theory is similar to what I discussed a minute ago. It is over some density contrast, you integrate over excess matter parts, but you should be careful, because typically people assume these are some spherical objects, blah, blah, but pretty much everything is stochastic in such processes. So if you assign probabilities to the shape of these collapsing objects, you should do the proper integrals from the beginning. Like, I mean, you have like triaxial, it could be a bit ellipsoid shape. When it's ellipsoid, the collapse changes, it becomes a bit harder, blah, blah, all these details. So you integrate some region, and you have a window function, and then you try to have some quantity, and you expect this quantity to be larger than some threshold value, but then you should be properly taking into account all the details of this relation, okay, to do it non-perturbatively. Anyways, I would like to just come to the final point. It seems when you take just Gaussian or standard theory, which means just this Laplacian times zeta, like structure, and neglect all these nonlinearities, you end up with such a relation. This beta is the fraction of the universe that turns into a PBH for a given amplitude of density perturbation, okay? As you see in NG, non-Gaussian or nonlinear, you can interpret. In order to produce same beta value, as you see, you go to a larger value of density perturbation, which means since PBH is a really requiring large density perturbation, at these scales, we need some really proper treatment of this problem. And we understood that after this exact numerical work, when you assume only Gaussian guy, it is a bit harder to produce primordial black holes than the earlier estimations. Okay, so this non-Gaussian or non-linear treatment tells you that in order to produce same beta, same fraction of the primordial black holes in the early universe, in all these plots you see, you need a bit larger amount of density perturbations. Okay. Okay. Now let's try to. How many minutes? Okay, I have, I guess, 15 minutes, right, Soner?
Yeah, 15 minutes plus, as you wish.
Okay.
As Seshgajan well knows.
Okay. Plus whatever, like it.
Okay. Okay, I'll try to cover up in 15-20 minutes. I think it's enough time. So here, this is a bit slightly same story. these are some bounds I'm not expert on. Again, these are I took from some people who are expert of this, but again the logic is same. Some fraction of the amount of primordial black holes with respect to cold dark matter, and some bounds on it, and as a function of mass of the primordial black holes, which means, like, let's go a simple example. Let's say we know solar mass is 10 to the 30 kilograms, which is 10 to the 33 grams, right? Here, at these solar energy mass black holes, you cannot produce the energy density more than 10%. You cannot make primordial black holes more than 10% of the cold dark matter. Okay, so these are such bounds. What you do is the following. This is the current universe bound. Then you go to early universe, like because remember I said that primordial black holes are non-relativistic objects, and during radiation domination they grow with respect to radiation. So when you form them during radiation domination, these are all corresponding to the scales that these perturbations enter the horizon back in radiation domination. Which means if your perturbations enter the horizon early, which means you have a smaller mass, you have more time to grow in energy density, right? Because even if you start with beta's tiny number, for these guys, you have more time to grow with respect to radiation. So that's why there's this tilt, almost going with the scale factor, okay? So after you find this beta, remember beta was this guy, which is connected to some inflationary or density contrast parameter. You invert this relation and find what would be the corresponding inflationary scale or inflationary perturbations for a given scale K for this scale. So this beta is the value, and these all m's, remember, corresponding to some scale, because PBHs are forming for a given scale, because it's a really nonlinear collapse, which means you convert this at the end of this relation constraints on the primordial inflationary fluctuations as a function of the mass or wave number, okay, of your inflationary quantity. As you see, I discussed a minute ago, you need, so there were two things I discussed. One, when you would like to produce primordial black holes, right, you can have non-Gaussianity, primordial non-Gaussianity. It is coming inherently. It has nothing to do with the gravity discussion. This is coming from your fields. This is coming from the high energy physics. This is coming from your UV complete theory, let's say. You can produce these primordial black holes from Gaussian, maybe non-Gaussian interactions, chi-square or cubic non-Gaussian. And you see, you can produce more black holes with large number of non-Gaussian. So you can have a smaller amplitude fluctuations, but you are more efficient in the PBH amount. Another thing was this. This is coming from directly gravity. There is no assumption. This is just the Einstein equations, actually. There is nothing hidden. There is no model assumption. There is nothing phenomenological here. It is exactly one-to-one GR equations. This is what you solve in when you evolve your density perturbations, okay? Which means this is inherent. When you would like to produce primordial black holes, this is just the nonlinearity of gravity. You cannot escape from this. But this is related to your high energy physics theory. Whatever model you have during inflation and you produce these PBHs, it changes depending on its properties, statistical properties. You produce more or less primordial black holes, okay? So this is exactly saying that, you see, when you have Gaussian fluctuations, you need a bit larger amplitude fluctuation. But when you have your high energy theory, let's say, have a chi-square like fluctuation, like in axion field, right? Because remember, in axions are coupled to gauge fields by quadratically, right? Phi, F dual. In each F, we have one gauge field. So you source axion by two gauge fields, which means you multiply these guys in a way, or you convolve them. Okay, so that's why even with smaller amplitude fluctuations, you can produce large amount of primordial black holes, or you can constrain them to a smaller power spectrum. Okay, too much discussion. I'll skip this slide because otherwise impossible to finish on time. Okay. Okay, after all this PBH chaos, like intriguing introduction, now you may ask the following question. Okay, you told us we need some large density perturbations to produce primordial black holes. And interestingly, they could be really the dark matter, or they could be some fraction of our universe. But gravity is nonlinear. Of course, there are higher order perturbations. You discussed that large order scalar perturbations are making hard to form these PBHs, but could they also source gravitational waves? Yes, they can. At linear order, scalar, vector, and spin 2, all these spin fluctuations decouple because it's just a conservation of the angular momentum. But starting from nonlinear perturbations, higher order perturbations, cubic interactions, right? You start to source with scalar perturbations the density gravitational waves as well, which means when you have large density perturbations, you can source gravitational waves as well. So this also has been studied some time ago, nonlinear fluctuations during inflation. People study this in generic, how you have, let's say, scalar, vector, and tensor fluctuations, and you can perturb them either quadratic level, which makes them, when you vary the action, it becomes a linear equation of motion, or you can perturb them to cubic order, which is the includes the interactions of the fields, and then you can check the equations of motion much more complete manner. But since fluctuations are so tiny, typically you deal with the just first order fluctuations. But if you would like to probe such interesting cases that like a large amplitude density perturbations or PBH formation, you should be considering also this higher order fluctuations. So let's come to the this problem. At linear order, this is 0 because we know that they decouple. This S term, which is source term, is 0. But then you just you can derive this equation just from the either you start from the Einstein equations like G mu nu T mu nu, or you can write it as from perturbing your Lagrangian to cubic order. Okay. So remember, I mean, this is the equation we are familiar with. What is that? In some, let's say, conformal time units, whatever it is, in an expanding universe, this is how gravitational waves move, propagate freely. And this is 0, right? This is just the thing. And the solution of this is just a plane wave. And if the universe is expanding, it decays with the scale factor. Same story. Nothing I would like to add. But if you have large density perturbations, starting from quadratic order, this source is quadratic in the density perturbation, scalar perturbations, start sourcing these gravitational waves, which is very interesting. So as you see, all these zeta, for the people who are from the field theory background, you could immediately remember, this is just in a position space P, K minus PP, which is just convolution integral. So it's a local interaction. But here there is this derivatives on them. So the scalar perturbations derivatively coupled to the gravitational waves. So you need a kinetical term for them. And then the same story, what is it? Omega gravitational waves. How much energy, how much gravitational waves you produce is proportional to 2-point function. And it is proportional to, if you would like to remember this standard green function, we know from the second year of the undergrad courses, right? We have a source term and we find the green function of this thing, right? And we convolve them. And the time is the only variable here, right? For a given K. So you find the green function of some differential equation just from coming from the homogeneous solutions. Then since you have a source, you just do the green function method, right? You convolve them. So this is t minus tau, some tau 0, let's say, tau 0 minus tau, and this is also tau. And then you convolve over time, and then you compute, square it, because it's a 2-point function again. But this corresponds to zeta to the 4, which is called something called like 3 spectrum, like a 4-point function, okay? So I could say the following. This is just inevitable consequence of having large density perturbations. This is another thing you can escape. Whenever you have zeta, you have this inevitably. And when your zetas are large, there's a chance that you can see these signals. So this is also just GR. These equations are just pure GR. If your zetas are large, you see them. That's the whole game, okay? Whole thing. Okay, so this calculations has been done many years ago. People find these gravitational waves or whatever. What I was curious was the following thing. Let me just take you back to this story. For these scales, I mean, can we see any signal? You see, it's a just vast desert. We don't see anything. We know nothing about these 40 faults. Can we see anything with the help of these gravitational waves about these scales, maybe high energy theories? So let's assume there is some interaction. You can also take either both Gaussian and non-Gaussian. So I decided to study both Gaussian and non-Gaussian and try to see what would be if there are some fields at those scales and they are active. They are really some way enhancing our perturbations. I compute a 2-point function for the Gaussian, and this is, imagine a non-Gaussian part or interaction part of the some field at some given scales much smaller, and then let's see if we could see these signals. And then this game turned into a bit more joyful thing actually. Earlier, people were computing this. Remember, if everything is Gaussian, all higher order correlators could be written in terms of power spectrum. Remember, when you have Gaussian random variables, 2-point function, 4-point function, 6, 8, whatever, is just written in terms of power spectrum, right? And every odd guy just vanishes. So here we have a bit spice in this game, and it's expected if your fluctuations are a bit larger, maybe there is some field interaction or whatever, some richness, something different. It doesn't have to be, we don't need to know the exact structure. You will see, even if you describe the simplest way, we will see some signs of it. So that's why this is very interesting. We will see something very different from the Gaussian ones. And then I divide this into two groups. So we will gravitational waves from some density perturbations. This is coming from GR, but again, if these fluctuations are large, we will see them in interferometers. Some Gaussian nature, Gaussian statistical property fluctuations, and some, let's say, some interactions, maybe some fields are there, or maybe some quantum diffusion, or many more possibilities at high UV scales. And these are coming from some interacting theories, let's say. Okay, so the game is the following, guys. Let's turn this into some diagrammatic game. What is it? There is H, right? This is the Hij part, gravitational waves, and it is coupled to, remember this, H coupled to two zetas, which are scalar fields. Let's say just this game, graviton, two scalars, and then interaction is indicated by like this some 3-point vortex. Okay. So in the standard game, you have two copies of this guy. You see my cursor, right? Do you see?
Yeah, we see.
Oh, sorry. So you copy this like in optical theorem or whatever, right? You square this result, and you end up with, this is the only diagram for Gaussian. That's it. You have a momentum circulating in this loop, and you have a graviton sourced by 4 legs of zeta. So it's proportional to, remember, pH proportional to p zeta square for Gaussian. But some interactions have much more rich consequences. So the game is, you have square of this, but you can square order of this as well, which is called FNL square, like second order in these interactions. So the game is the following: contract the legs, scalar legs. That's the game. Okay, 2 of these, 0 of these, or 2 of these, or 4 of these. So at quadratic order in this, you can have these two diagrams. I always say everywhere, I give these names for them because it was a power spectrum is being modified, and I call this hybrid. And I call this because it was a really Jewish shape. I call it walnut. So these are the only two diagrams contributing to FNL square order. And then FNL to the 4 order, when you go to the, if you have really large non-Gaussianity, you end up, or interactions are really strong, you expect to have such diagrams. Okay, so this is turns into a diagrammatic thing, and then you compute, you do these integrals in momentum space. You may ask, okay, boy, why didn't you take into account these diagrams as well? There are richer options to contract these legs. You see, there is this option, there is this option, there is this option. Okay, the reason is, for these ones, if you see, the momentum in this part is just 0. Okay, did I zoom? So this part, okay, so this part, this propagator in this leg is 0. But remember, the coupling is through K, right? You cannot have a zero momenta in any of these legs. So these diagrams will give automatically zero. These guys are just vanishing. This is also here. You see, there's a zero momentum circulating in these legs. And this is vanishing because of the angular momentum conservation. Like if you cut it off, you see you have a spin 2 particle and you have a spin 0. This, because of the symmetry, this doesn't contribute to the 2-point function. So in short, this is the all topology you have for this complicated story, okay? These are the topology. This is reducible because this leg and this leg could be dropped to a single power spectrums, and this could be reducible to one loop diagram. This could be but these two guys are honest 3-loop calculations, 3-loop diagrams. This is planar and this is non-planar. That's why I give these names to these guys. And these are also 2-loop diagrams, and this is just one loop. By loop, I'm not using it in the QFT sense. I'm not doing anything Feynman, like a propagator correction. I mean, kinda, but it's not a renormalization calculation in a way. This is just a classical calculation at the end of the day, okay? You have some source and you try to, some source from the density perturbation, and you try to produce gravitational waves through it.
Is it really 3-level?
Which one, Hocam?
I mean, you have a one loop for the Gaussians, you have a one loop calculation.
Yes, but this loop, Hocam, is not a renormalization loop, I would like to say. This is a loop.
That is true, but do you is this a divergent there? Is there a UV divergence?
No, there's no exactly. There's no UV divergence.
Okay, no. So then you don't need to normalize.
Exactly.
Normalize it all.
Exactly. You don't need to normalize this. Exactly.
Okay.
Otherwise, you have to exactly. In the UV regime, this doesn't because of the green function. It never diverges. It never diverges. And interestingly, actually, this is an interesting point. I checked. I didn't write a paper, but I should maybe have done this because after me, there was a group writing in Japan. In the infrared regime, due to just causality, you know that these gravitational waves are scaling with F cube or K cube. This is a universal thing. And it's funny, it also works for the phase transitions. If you produce phase transition idea is the following thing. You again have you see Hij couples to Tij. So in your energy momentum tensor, you need some anisotropies to source these gravitational waves. It happens also in phase transitions because it's an anisotropic process. It's same because there's a scale, given scale that phase transition happens. If you go to infrared regime of that, much larger wavelengths, like soft theorem, if you wish, but not, I don't want to use the soft theorem word because it's a bit, there's much deeper meaning than this, but infrared regime, infrared, it behaves like K cube, just coming from the causality, and it's satisfied by this green function, but it is just basically coming from the causality, I would like to say. And the reason is very meaningful. The reason is when you go to the extremely large scale, the small scale fluctuations are just a white noise to you. And this white noise is behaving like a 1/volume, and 1/volume is just K cube because it goes like lambda cube. That's the beauty of this result. It just self-checks itself. Okay, there's something at small scales maybe happening, and you can see it only if you are in the, you understand that if there is this K cube like thing. So it's so small scale, it's like in your TV's white noise. Okay, it's a small scale, but you have much larger wavelength or whatever. It still leaves its mark, but it's suppressed with the causality. Okay,
John, when you say like white voice, you mean like constant in the Fourier space?
No, I mean it's more like assume you have a high frequency signal and you are in the large frequency. How would you see the effect of it on a large wavelength? Like large wavelength, you have a little bit jitter, right? And imagine your volume grows. You look at larger and larger volumes, right?
So yeah, in the frequency space, like it would be like finer and finer detail that I will no longer see. So it would be like constant in the frequency space.
It would not be seen, but it vanishes. In large scale correlators, it's suppressed. If you go to infinity, you don't see it, right? Because it just averages out. You don't see anything. It's zero. Yeah. But the thing is scaling. Scaling is K cube, or it goes like a 1/volume. That's what I'm trying to say. As you become, if you do your kind of probing scale, whatever frequency you look at, the scale you look at, goes larger, right? This high momentum processes in your correlator at large correlator is still there, but its scales contribution goes like 1/k. It becomes smaller and smaller and very fastly, because in volume it just becomes a little bit jitter. That's what I try to say. That's what I'm just trying to say. As the scale changes, the scale, the correlators are changing with the volume. That's it.
So this is not. I was probably it is not then what I'm asking, but let me still ask. So this is not somehow like similar to Weinberg soft photon stuff, is it? Like, do you have some soft gravitons?
I think, okay. I am not sure that, so Weinberg's soft theorem is saying basically what?
Well, essentially, yeah.
Actually, I think we can ask even a simpler question. Like, do we have any IR divergence?
No, there is no IR divergence because the source is finite in a given scales. Okay, there's no, the source doesn't go to at infinity. No.
We need IR divergence for soft theorem, right?
Yes, if it was there, probably.
Yeah. Okay.
Exactly.
Okay.
So no
I mean, since you have already said that there's nothing remaining at infinity, I would suspect that then there won't be any.
So there is no IR divergence. There is no UV divergence. What kind of equation is this? Like.
But it is for some scale you produce these fluctuations. You don't produce them for a. You cannot go to infinity UV. You cannot go to infinite IR because inflation starts at some scale, right? I mean, you can never be able
to. You have this because you're okay. So you have an effective theory in some sense.
Yeah, but that means you should have a regulator, like a cutoff somewhere.
Exactly. You can imagine. But what I'm saying is, inflation is also kind of effective theory at the end of the day because we don't know of the really UV part of the inflation. I'm saying that inflation is happening around some scales, and only around some of these scales we could see some signs or signatures of such type.
I agree, but like if you take like during inflation, let's assume like universe is almost like ds de Sitter, right? Yes. And the recombination would be like the boundary of the de Sitter.
Yes, but in de Sitter, pure exact de Sitter, you have IR divergence. Yes, because
I was about to say that.
It grows to infinity, or it scales with 1/m² like thing. Yes, correct.
But in this situation, you say you somehow don't get IR divergence.
No, this is exactly for a given some scale. There is nothing diverging here.
Okay. Anyway.
Just one further small comment, Caner, before we give you a chance to complete. These so when you draw these non-planar diagrams, there is this Tihouf double line notation or
no, these are Caner's diagrams. People make fun of me. Actually, some QFT people, a bit. I mean, not QFT people, but I had in Prague. There was this lady, Korean lady. She was very good. She was the student of the Woodard. You know this Woodard guy. They compute the renormalization of the graviton propagator. And when I drove these diagrams, each time she was getting crazy because for them, like, there is this UV scale and IR scale. There's something should be divergent. I should do proper renormalization, which I don't. But I explained to her, like, this is not a renormalization calculation. It is just my bookkeeping. Honestly, my bookkeeping. I mean,
but still, you should be able to draw these with double line notation, probably.
What is double line? What is double line?
So, well, for each line, you draw double line. So that will give you the non-planar topology in a very nice manner.
Do you see this corner? I mean, non-planar topology is for here, right? I mean, you cannot track these legs through the plane. You have to go up or down the plane. So it's a very complicated thing. But
right. So there is some theory for this non-planar diagrams, which allows you to take the large N limit of the gauge theory, but probably that is not relevant for you. However, still, it might somehow be some sort of a useful thing.
I see.
Yeah.
I don't know
Jana-
this bubble line actually. Okay, I really don't know. Okay.
Jana, before you move on, can I also ask another question?
Yeah.
So you said you are doing this calculation at a scale, right? I think you take it as an input, like you choose a scale.
This is just generic. These P and Q are general wave numbers. They are just momenta, yeah. But I'm
Yeah,
saying,
but like we earlier said that you don't like go consider like IR or UV, like you effectively have a cutoff or effectively have like a regulator, like
Yeah.
effectively something like that. Did you consider changing it and how it like, did you basically do any RG in this formalism? Like change the scale at which you look at these diagrams and see how it affects the.
okay. This is okay, but this is not like a conformality or whatever. Like this is just the following thing. You have inflation. You know what wave numbers these guys are corresponding. Okay, like you know what is the these are just physical scales we see in the sky. These are just that. Okay, then. At some of these scales, we measure it in the sky, CMB-like structures. CMB, we measure these correlators, these multipoles, okay? And then we convert them to a momenta, and then we understand typical inflation thing. And it's a linear physics there. At much smaller scales, it's super nonlinear. We don't know anything about that. We don't know even how to compute because it's extremely non-perturbative thing. So there is like this is not like I don't know if I'm understanding you correctly, but this is not like that's the funny thing about inflation. There is like a universal clock in this de Sitter thing, and we are working on some specific momenta, and we normalize this momenta with respect to some scale factor we choose now as one, and then we take the largest scale of our observable universe as some whatever scale, and everything smaller than that, because outside is of course non-causal, everything smaller than that to some degree. But of course you cannot go extremely high momenta as well because of the obvious reasons. So that's the game. It's slightly different than the, I think, but I don't know, this is my understanding.
Yeah, maybe I wasn't clear. Like when I said RG, I didn't mean its application in CFTs or in QFTs, like forget about any quantum filter or anything. Like you said, you take like a universe, right? Like some scale at the universe, and you don't consider outside of it for causality reasons.
Like black
right?
hole. This is the horizon. This is the horizon, exactly. Outside the horizon is not causal.
Yeah. Assume you just mathematically change the horizon. Like horizon is, let's say, it's like a momentum.
That's a good point.
Lambda, and you say
but
horizon.
That becomes a different theory. This becomes a different theory.
Yeah. Okay. So different theory, but let me change it from, let's say, lambda to a times lambda, and a to be very close to 1. Like I'm just an infinitesimal change in the horizon. So in a sense, I have like continuous line of different models, right, for different horizons.
Exactly.
So I'm thinking
a set of models. Huh?
Exactly. So when I said RG, I meant actually something like that, like in flow between these theories.
Yes, correct. Yes, you can do that.
Anyhow, it may be quite redundant or insightful. Okay, sorry for the interruption.
No, I mean, that was, I don't know, yeah. Okay, anyways, okay. I'm not gonna talk too much about this part. I'll just come to the results, guys, because I think we already passed 5-10 minutes. So I studied for different interaction levels, I could say, okay, and different diagrams: hybrid, walnut, reducible, planar, and non-planar. And I found that for relevant regimes, typically FNL square order corrections are dominant. And I studied this for different types, different scales of interferometers. And I realized that these non-Gaussian perturbations could produce gravitational waves more efficiently because of the higher contraction rates. And also, since there is an interaction and there's a convolution, the peak of this interacting theories are peaking a bit higher momenta. So for large width guys, you don't see, it's a bit observational thing. I'm not sure how much people are interested, but let me just say a few words and finish this talk. So assume you have log normal type of power spectrum, like it's just a log normal bump. Some amplitude log k over k star divided by sigma 2 sigma square. Sigma is the width of your signal. Let's say it's 1, which means corresponding to a 1 e-fold of inflation typically. And then you see, I take P zeta is the total density perturbations. Let's say Gaussian fluctuations are shown in blue. The interacting perturbations are coming from green. And then you see they are more or less same amplitude. Actually, with usual non-Gaussians are a bit smaller. But then let's see the gravitational wave production. It seems, as you see, gravitational production is dominant for the interacting guys with respect to the Gaussian ones, even though their amplitude is similar. So that's one interesting result. Another interesting result was this. When you have a really narrow spectra, because you see it becomes almost like a delta, some peak, whatever. But when you have a convolution, it becomes like a you change the power spectrum. Like you have 2 of these momenta, so you can peak a bit higher frequency, and it will be visible. So you see, this is the omega GeV total gravitational waves, and when you have it all Gaussian, this is the peak. This is the standard story that everybody does. But even if you have a subdominant fluctuations, as you see here, you see you can have a second peak around here, and you immediately realize that, oh, I have a double peak. I wasn't expecting that. That should be coming from some interaction. Or even if your interaction is too tiny, this parameter is tiny, order 1, if you have a strong, really strong gravitational wave interferometer, you can see it from the UV bump. Because why it's UV? Because you convolve 2 momentum modes. In the Gaussian one, you just solve that. But in they are just there is this one loop, like momentum loop. But in the non-Gaussian one, there are more contributions, and convolution makes this fluctuations more fuzzier, and they can peak at higher frequencies because you have more modes. Like assume you have some delta-like function, right? When you convolve it, it becomes milder, and each time you do it, you can go higher and higher frequency. So if you have a good, really gravitational wave observatories, it's remarkable. You can probe FNL order of 0.1 to 10, which is remarkably better than the next generation CMB analysis. But of course, this requires a bit of visual thinking, to be honest. And final work, I was a bit depressed that my works in 20 years, will anybody care, give a shit or not? So I was thinking like, maybe I should do something beneficial for the human beings. And I just try to do this paper with people using the cosmological observations, stochastic backgrounds, and CMB spectral distortions. This is just the chemical potential mu distortion. We do this paper. Actually, after that, I give up working on primordial black holes and any other story, because this was the paper for me. We show that whatever fluctuation type you have, statistical properties, you can always, because remember, with non-Gaussian fluctuations, you will be able to escaping all these constraints. But with this next generation perturbations, next generation cosmological observables, stochastic backgrounds, gravitational waves, and the CMB's spectral properties, we will be able to probe small scale fluctuations from inflation so well that there is almost no way escape for primordial black holes. If we see no signal, that's the end of the game for any PBH larger than 1 solar mass. So you see here in this plot, P zeta, the primordial density perturbations. In x-axis, you see the scale, momenta scale. And on top, you see the primordial black hole mass, seed of it, when they are first formed. And on top of it, what is the today value for them? Why I said the paper for me was the following thing. If we see any signal in these guys, it's remarkable. It's beyond standard model for sure. It's really interesting, and it's extremely exciting. We could say a lot of words, and we could get the signal much better. But if we see nothing, nothing interesting, first time we showed that you can constrain any PBH larger than 1 or 0.1 solar mass, forget about them. There are no such things. And this is true independent of they are formed by Gaussian, non-Gaussian, cubic non-Gaussian, whatever crazy model you have, guaranteed. And for also, this is independent of any astrophysical processes. Like maybe you claim that maybe there's a merger, maybe they are collected, clustered around each other, so they escape from this. No. Why I'm saying is the following thing. The mu distortions are sourced by primordial density perturbations. And if this number is, if we could really probe them well, we could immediately constrain this guy very strongly. So these are just cosmological bounds, nothing astrophysical, nothing phenomenological, nothing maybe a little bit factor of 2 there. No, it is there. There is guaranteed no escape signal and very robust. I think in this field, one of the most robust papers. I don't want to be undervoice this. This is really one of the most robust papers, and this is also inevitable because this is just GR. When you have these density perturbations, even inflation or not, whatever you produce PBHs, you cannot escape them nonlinear level gravitational waves. And when you have these gravitational waves with these very strong next generation stochastic backgrounds, they have to be there. Not maybe, not possibly, not I can escape them with some astrophysics or whatever. No, just cosmologically, global signals, we probe them extremely, extremely well, and the conclusions are conclusive. So it doesn't care about all these details. And if they are there, that's also remarkable because we will be able to see their signals in the stochastic gravitational waves. Plus, maybe they could form the supermassive black hole seeds. It's interesting because even if primordial black holes are extremely negligible fraction of the energy density, they could form the seeds of the supermassive black holes now in the cores of our galaxies. And even if this is the story, we will be able to see them. There is no escape. So if they are there anyway, we will see them. Otherwise, their energy density is much less than 10 to the minus 10. Okay, so they are not there. These are the conclusions. I'm done. If you have any questions, we'll be happy to discuss. Yeah. Talk.
Jana, thank you so much for this great talk. Is there anyone in the audience who would like to ask a question or have comment? Okay, then I will stop recording them. We can have an informal chat.
Caner, how is all this related or possibly related to dark matter?
For PBH, you mean, Hocam?
Yeah, for PBH.
Huh. Okay, just 1 second. So the story of PBH is, where did I put it? Here. So there are two regimes that PBH could be some fraction of the dark matter, which is why people go crazy and publish over 500 papers in last 2-3 years about this topic. One is this one, you see, around 10 to the 34 grams, which is 10 solar masses. There was people claim that maybe these black holes are coming from the primordial black holes. Some of the LIGO detected black holes are maybe primordial origin. That was one thing, right? And there are no, current bounds are still allowing some percent level or a few percent of these cold dark matter could be PBH still, more or less. And the other one is this 10 to the minus 12 solar mass range, typically this region. This is still debatable, this bound. That's why we put it in dashed. This region, you can produce almost all PBH in terms of cold dark matter. This part has to leave some signs on the pulsar timing arrays, nanohertz scales. Maybe you heard there is this nanograv experiment now recently announced, some stochastic gravitational waves, possibly coming from astrophysical sources when the supermassive black holes merge. But for LISA, these scales, this is the next 20 years mission. So in the next 20 years, probably we will be seeing this and we will have a conclusion. So how PBH could be the dark matter is this story. I will go back. This one.
You mean for this each PBH or for a whole ensemble?
No, whole.
For the entire.
Exactly.
So one PBH could have a more dark matter than another, or some.
Yeah, like you can think that. Assume we have a bump, like some enhanced fluctuations, and we produce with this, let's say, this axiom model or some way. We have some, let's say, around solar mass or 10 to the 22 grams, some enhanced fluctuations. Let's say these are the bounds, but assume I have a really bump, like something like this. Let me just go back to here. Like, let's take this one. Okay, you have a standard inflation, but assume you have some bump, let's say, some enhancement of fluctuations. This is at pulsar timing array scales. And then immediately you go, like these scales are corresponding to primordial black holes of mass 1 to 100 solar masses. So you go back here, you go here, around here, you produce some bump here, okay? You produce a bump. You integrate this area, beta, and then you of course, their energy density grow in time. So you compute, I didn't have an exact relation for that, but it corresponds to here, let's say. You produce lots of primordial black holes. So in observable universe, I think the total mass is 10 to the 57 grams or so. I'm not exactly sure, but cold dark matter is about 10% of energy density, 30%, whatever. So 10 to the 56 grams. You see, if this is the mass, typically 10 to the 33 grams, you have 10 to the 22 order of solar mass black holes. So they are everywhere. They are everywhere in the galaxies, halo, everywhere. So it's just instead of the particle dark matter, you have these primordial black holes, much larger guys, and that's it. They behave like dark, and it makes sense. They are not too much interacting because gravitational interacting, their self interaction is tiny. Blah blah. All this dark matter story makes sense because they don't radiate other than accretion. Blah blah. So
There's
they think that
there's no Hawking radiation for BBA.
that's a great point. Yes, but Hawking radiation is only making sense for light black holes, right? Because if your black holes are too heavy, right? Because Hawking temperature goes inversely with mass, so you cannot radiate much, and it goes like T to the 4, so you cannot. So only black holes whose mass is 10 to the 15 grams or less, Hawking radiated. Any black hole larger than 10 to the 16, 17 and more, they are cold and they don't too much. Even now they are fine. So Hawking radiation is valid for the guys here, okay? Yes.
By the way, that Hawking's law, is it valid at early universe as well? Like, does it energy dependent? Like that law that we use, you know, it goes like inverse temperature, etc. Like, because I really don't know much about it, like how it is derived, what are the assumptions. Like we are using it today in universe, but can we still use it in early universe during inflation time, for example?
It's probably a very difficult question. I don't know.
I mean, during radiation domination, yeah, why not? I mean, you use, I mean, most of the time that the black hole spend is matter dominated array at the end of the day, because redshift around 1000 or so, 3000, we pass to the matter radiation equality, and most of the time is matter domination. So matter domination is there is nothing, just dust. So they, yeah, I think, yeah, the Hawking equation is more or less same. And for light, only light ones radiate, and in the end of their life, we know that, you know, there is this gamma ray radiation from them because their radius shrinks, blah blah. But for heavy ones, it's almost zero because their temperature is also goes to zero. For heavy ones, it's almost zero. They don't radiate much. They are stable whole age of the universe. Okay, I paused sharing.
This is interesting.
Okay, let me stop the recording.